Welcome to part 3 of week 1. Hopefully you've had a chance to look at all of the exercises on bases and that you're fairly familiar with those ideas because we're going to be using them to explore the ideas of topologies on infinite spaces. So you might have noticed that all of the examples that we've looked at so far of topologies have been on finite sets. You've been able to count, if you wanted to, all of the elements in any of those sets successfully. You've been able to end your count. But we did look at some examples of infinite sets at the beginning, and so now we're going to be thinking about what a topology on one of these infinite sets might look like. So I think the most illustrative way to do this is maybe through an example. So let's take a look at a pretty basic infinite set, the real line. So the real line consists of all of the points are going to be real numbers. So for example, we might find 0 here, 1 here, 1 here, pi somewhere out here, negative 100 somewhere over here, and everything in between. So 1/2, 0.10101010, and so on, and anything else. All right, so all of these numbers, this is a pretty big set. How do we topologize it? That's the question we want to answer. Well, remember that when we're thinking about topologies, we're thinking about what are the open sets. And you might already have an idea of what an open set should look like on the real line because you've probably already heard of open intervals. So these are intervals like A, B, where A and B are real numbers. So for example, 0, 1 is an open interval, which is going to be the set containing all of the numbers from 0 to 1. So all of the numbers between 0 and 1, not including 0 and 1. So that's what these curly brackets mean. They mean not including the endpoints here. So for example, 1/2 will be in this set, and 3/4 will be in this set, and 0.9899996, whatever, that's going to be somewhere over here. But 0 and 1 will not be in that set. So you've probably seen open intervals already. Now, consider the set of all open intervals of the form AB. The question is, do they satisfy the requirements of a basis? So to answer this question, all we need to do is check all of the axioms. So the first axiom is the empty set. Is it in the basis? Well, I can write the empty set as the open interval 0, 0. I hope you'll agree that this interval contains 0 elements and therefore is the empty set. So that one's done, we're good. The next axiom I need to check is that every point is contained in an open interval, and well, that's easy too. So if I have the point P, then that's going to be contained in the interval P minus 1, P plus 1. Great, so we're done there as well. And now finally, we have the more confusing one, which is if I have an interval AB and another interval CD, and I consider their intersection, then if I have a point, let's call it P, inside of this intersection, then there's another interval. So an interval, let's call it IJ, such that IJ is contained in the intersection and P is contained in IJ. Okay, so how do I check this? Well, really all I need to do is think about what this intersection looks like. So I claim that there are actually only 4 possibilities. Actually 5, sorry. There are 5 possibilities. So the first possibility is that AB and CD don't intersect at all. And then there's no points to check, so this is vacuously true. Otherwise, we get 4 possible cases, so I'm just going to draw those 4 cases out for you, and we'll see what happens. So I could have A, B, and CD overlapping like this, like this, like this, or like this. Okay, and so let's take a look at what those intersections are. So the intersection here is actually going to be an interval itself, CB. So if I have a point inside of the intersection, it's going to be contained inside of the interval CB, which is also contained inside of the intersection. I think you'll agree. Okay, so the same thing is going to hold true here, except that the intersection is now CD. Here, the intersection is AB. And here, the intersection is AD. So in all possible cases, this axiom is satisfied. So we've answered the question. The answer is yes, they do. The open intervals form a basis on the real line. Great. So if I have something which is a basis, then it must form a topology as well, right? I can form a topology out of the basis. So the question is, what topology is going to correspond to the basis consisting of all open intervals? So what kinds of things are going to be open sets inside of this topology? Well, we already know that the intervals themselves are going to be open. We also know that I can take, a bunch of intervals. So for example, I could take 1 to 2, 2 to 3, and 3 to 4, and I could take the union of these 3 intervals, and that's going to make an interval something that looks like this. Right? Here's 1, 2, 3, 4, and it's going to this sort of set that contains all of the points between 1 and 2, between 2 and 3, and between 3 and 4, but not including 2 or 3 or 1 or 4. That's going to be an open set. Here's a question. Is the interval 1 infinity an open set? So this interval means the interval which starts at 1, but not including 1, and extends all the way down the line. Is that an open set? Do we want it to be an open set? Here's an even better question. Is the entire real line an open set? Do we want it to be an open set? Well, we definitely want it to be an open set, because you'll remember that in the definition of topology, we want the empty set and the entire set to both be open sets. So we need to be able to make the entire real line out of a union of intervals. Is that possible? Well, let me try to write down a list of intervals that will capture the entire real line. Well, maybe I'll start at 0, 1. Okay, well now I need to get 1, so maybe I'll do 1/2. Well, I need to make this really big, right? Because I need to include like all of the real numbers, so maybe I'll go 500 million, 1,000 million, that's a billion, 500 trillion, quadrillion. It seems like I can't actually write down a list of intervals whose union is going to be the entire real line. So I need to fix something here. In particular, what I need to do is I need to make a small fix to the previous definition of topology. So this is our previous definition of topology. We had the 3 axioms. The empty set is in T and so is B. C and D are in B, then so are their intersections and their unions. Well, the problem is I will never be able to build the entire real line if I limit myself to pairwise unions, meaning I won't be able to build it if I only take unions of 2 intervals at a time, right? I can't come up with 2 intervals whose union is the entire real line. What I need to do is I need to change this to be a bit more generous. Given an arbitrary collection of sets in B, their union is also in B. If I change this axiom to this new statement, then instead of taking 2 intervals, I can take as many as I want, including infinitely many, and then their union I declare to also be in B. Sorry, to be in T. This is supposed to say T for topology. Okay, so I can now take an arbitrary collection of sets, and I can take the union of all of those things, and arbitrary means possibly infinitely many. So let's take a look at the real line. With this new definition, is 1 infinity an open set? Well, yes, because I can come up with the following, right? I can just take 1, 2, 1, 3, 1, 4, 1, 5, and so on and so forth. I can take this infinite list of intervals, and I can take the union of all of them, and that will be 1 infinity. And since I constructed this interval out of my basis elements using the closed under unions definition of a topology, this thing will be an open set. I can also ask, is the entire real line an open set? And the answer is again, yes, right? Because I can construct this again. What do I take the union of? Well, I have different options, but I could, for example, take -1, 1, -2, 2, -3, 3, and so on and so forth. I can take this infinite set, and if I take the union of all of those intervals, what I get is the entire real line, which I can write using this sort of boldface R. Great, so I think what we've shown is that we now have this topology whose basis consists of all of the intervals. We had to amend our definition of topology in order to make the entire real line an open interval using that basis. And this example is sort of what all of these definitions are born out of. So you might be a little bit annoyed at me that I had to change the definition in order to accommodate this example, but really the definition was something we said, oh look, I have an example of this thing, but what is this thing I'm looking at? And then we came up with a definition to fit the example, and that's how it was actually done in math. So now what we have is a corrected definition of topology according to this example. So here's an interesting question that you might wonder. Are there other topologies on the real line? And you'll be able to find out the answer of this if you do the exercises. All right, in conclusion for today, in this first lesson, we've covered the definition of topology, the definition of a basis, and in the third part, the actual definition of topology. Now it's your turn, so take a look at the third set of exercises. You'll be working with infinite topologies now, which is very exciting. Hopefully you'll have a chance to do those exercises, and we will see you next week in the next lesson. All right, thank you guys so much. Bye.